Imagine a world where humanity finally cracks the code of limitless clean energy, where power plants no longer rely on burning fossil fuels or splitting atoms, but instead replicate the same reaction that fuels the sun. That's not science fiction anymore. That's fusion energy. And right now, the global race to build the world's first power-positive fusion reactor, one that produces more energy than it consumes, is reaching a critical moment. Welcome to Beyond Binary, where we decode the technologies shaping our future. Today, we're diving deep into one of the most complex, controversial, and fascinating scientific pursuits in human history: the race for fusion power, the recent shutdown that rocked the fusion community, and why that temporary setback might actually bring us one step closer to the energy revolution of the century. So let's start with the core idea. What exactly is fusion? Unlike fission, which splits heavy atoms like uranium to release energy, fusion does the opposite. It fuses light atoms, typically isotopes of hydrogen like deuterium and tritium, under extreme pressure and heat, around 100 million degrees Celsius, forming helium and releasing enormous amounts of energy in the process. This is the same process that powers our sun. Theoretically, it offers nearly infinite energy from seawater, zero greenhouse gas emissions, and minimal radioactive waste. It's the holy grail of energy. But there's a catch. To achieve fusion on Earth, we need to create a miniature star in a controlled environment, and that's extraordinarily difficult. For decades, scientists have been trying to achieve what's called net energy gain, where the output of fusion energy exceeds the energy required to initiate and sustain the reaction. Until recently, that goal was always just out of reach. Then, in late 2022, something incredible happened. The National Ignition Facility, or NIAF, at Lawrence Livermore National Laboratory in the US, achieved what was hailed as ignition. For the first time in history, a fusion reaction produced more energy than the lasers that powered it. It was a huge milestone, a scientific first that made global headlines. But here's where the story gets interesting and complicated. Despite that success, NIF's fusion experiments were limited to very small bursts, fractions of a second, and nowhere near continuous power generation. Meanwhile, across the Atlantic, the massive international collaboration known as ITER, based in southern France, was preparing for its own attempt to reach net positive fusion through a completely different method: magnetic confinement. Instead of lasers, ITER uses magnetic fields to hold a plasma, a superheated soup of ions, in place inside a donut-shaped chamber called a tokamak. ITER has been under construction for over a decade, involving more than 35 countries and costing tens of billions of dollars. Its goal is to demonstrate sustained fusion for several minutes, something no one has ever achieved. But earlier this year, ITER faced a major setback: a shutdown. Now, let's unpack what that actually means. In large-scale experiments like ITER, a shutdown refers to a full or partial halt of operations, either for maintenance, safety, or due to technical issues. Unlike a typical maintenance pause, a shutdown in fusion research is a big deal because these reactors operate under extreme conditions. Every component, from superconducting magnets to plasma-facing walls, must perform flawlessly under intense stress. A single flaw can delay the project for months or even years. The recent ITER shutdown was triggered after engineers discovered defects in key components, specifically in the cooling systems and sections of the vacuum vessel. These were not minor issues. The cooling systems, responsible for maintaining cryogenic temperatures for the superconducting magnets, showed signs of weld irregularities. In a machine designed to hold plasma at over 100 million degrees Celsius, even a tiny structural defect can become catastrophic. So, in mid-2024, the ITER organization announced a full inspection and temporary shutdown of assembly operations. This wasn't a failure. It was a calculated safety move. but it did have ripple effects. Construction timelines were pushed back, testing schedules delayed, and budgets stretched further. For context, ITER was originally expected to achieve its first plasma by 2025. But with this shutdown, that target might now slip closer to the end of the decade. Critics say this proves fusion is still decades away. Supporters argue it's just part of the natural evolution of an unprecedented engineering challenge. After all, no one has ever built a machine like ITER before. But ITER isn't the only player in this race. While the giant international project works through its engineering hurdles, private companies have entered the fusion arena with bold claims and innovative designs. Firms like Commonwealth Fusion Systems, Helion Energy, and Tokamak Energy are racing to build smaller, faster, and cheaper reactors. Helion, for example, has announced plans to deliver electricity to Microsoft by 2028 using a novel pulsed fusion approach. Their latest prototype, called Polaris, is designed to test direct energy conversion, turning fusion energy straight into electricity without turbines. Meanwhile, in the UK, the joint European Taurus, JET, the world's most successful tokamak to date, completed its final run before shutting down permanently. That was another important shutdown moment, but for a different reason. JET wasn't closed because of failure. It was retired after decades of groundbreaking research. In its final experiment, JET set a new world record, sustaining fusion energy output for over 5 seconds. That may sound short, but in fusion terms, it's a lifetime. Its data will now help guide ITER and future reactors. So when we talk about shutdowns in fusion research, it's crucial to distinguish between operational pauses, necessary for safety and progress, and end-of-life closures like JET's. Both represent transition points in the long arc toward sustainable fusion energy. And that brings us to an important question. With so many challenges and delays, are we really any closer to fusion power? Surprisingly, yes. In fact, more progress has been made in the last 5 years than in the previous 50. Advances in high-temperature superconductors, machine learning for plasma control, and precision engineering have accelerated development dramatically. For example, Commonwealth Fusion's compact reactor design uses superconducting magnets twice as strong as ITER's, allowing for smaller, cheaper devices. Helion's pulsed approach bypasses some of ITER's complexity altogether. Even Google has gotten involved, applying AI algorithms to optimize plasma stability in real time. The global fusion landscape is no longer just about one project or one country. It's a multi-front race, blending public funding, private innovation, and international cooperation. But all of it leads to one shared goal: the moment when a reactor not only achieves net energy gain but does so continuously, generating stable power that can feed directly into the grid. The next few years will be critical. ITER's shutdown is being used as a moment to rethink and reinforce, to fix design flaws before they escalate. Private fusion startups, meanwhile, are under pressure to prove their promises. Governments are doubling down on funding, and public interest is growing fast. If fusion succeeds, it could transform everything, from how we power cities to how we fight climate change. A single liter of seawater could theoretically produce as much energy as hundreds of liters of gasoline without the emissions. It's a technology that could end energy scarcity forever. But success won't happen overnight. Every shutdown, every inspection, every delay is part of a story much larger than any single experiment. The story of humanity trying to control the power of the stars. So the next time you hear about a fusion shutdown, don't think of it as a failure. Think of it as a recalibration on the path towards something extraordinary. Because one day soon, maybe within our lifetime, a light might flicker on somewhere in the world, powered not by coal, oil, or uranium, but by the same fire that burns at the heart of the sun. And when that happens, it won't just be another scientific milestone. It will be the dawn of a new energy age, one built not beyond reach, but beyond binary. If you enjoyed this deep dive into fusion's breakthroughs and breakdowns, make sure to subscribe to Beyond Binary, because the future of energy and the story of how we get there is just beginning. This is ITER's assembly hall in southern France, the massive tokamak and its modular vacuum vessel sections. Here is the National Ignition Facility's laser target chamber, where powerful lasers focus on tiny fusion targets. The Jet Tokamak Hall at Culham, a retired workhorse whose final runs still inform fusion research. This is Helion's Polaris prototype, a pulsed fusion device testing direct energy conversion approaches. Commonwealth Fusion's compact tokamak uses high-field HTS magnets, a smaller high-field path to fusion power.